All right, today we're diving deep into the world of software security. We're going to talk about the hunt for those tiny, almost invisible flaws hidden deep inside the code that powers, well, pretty much everything in our lives. It is a massive, massive challenge, but we're going to look at a really radical new way that researchers are starting to tackle it. So here's the big question, right? The software we all rely on every single day is just massive. I mean, think about operating systems, web browsers, the whole shebang. A single tiny mistake, just one slip up in millions of lines of code, can create a seriously dangerous security vulnerability. So how on earth do security researchers even begin to find that one needle in a digital haystack? Well, one of the most powerful techniques they use is called fuzzing. And it's kind of counterintuitive, you know? Instead of carefully testing software piece by piece, you just throw absolute chaos at it. You basically generate millions of automated, slightly random, mutated inputs and just flood the program with them, hoping one of them makes it crash or act weird. Because that crash, that often points you right to a hidden bug. You know, for years, fuzzing was this kind of niche art form. But then this one tool called American Fuzzy Lop, or AFL for short, came along and just completely changed the game. It was so incredibly effective that it became the gold standard, pretty much inspiring a whole new generation of security researchers. But here's the thing. AFL's incredible success actually created a totally new, unexpected problem. See, researchers loved it so much that absolutely everyone wanted to improve it. So they forked the code, which basically means they made thousands of separate personal copies so they could add their own unique improvements. And, well, as you can probably guess, that led to... Yeah, the researchers behind this paper put it perfectly. They said this enthusiasm resulted in an incredible number of mostly incompatible forks. And the analogy here is just spot on. Imagine if everyone was building their own custom version of a car engine. None of the brilliant new parts they invented could ever be shared or fitted into anyone else's design. You'd have 1,000 great ideas that could never work together. And this fragmentation, it became a massive roadblock for the entire field. It created these three huge problems. First, you just couldn't combine one researcher's great new idea with another's. Second, it was really hard to even tell if a new fuzzer was actually better or just different. And finally, trying to compare different tools fairly became almost impossible. The whole field of progress just started to slow down. So, what the community really needed was a fundamental shift in thinking. They had to stop building these custom, one-off tools from scratch and start thinking more like they were playing with, well, Legos. And that's where LibAFL comes in. See, it's not just another fuzzer. Instead, it's a framework. Think of it like a toolkit, or better yet, that Lego box we just mentioned. It's full of standardized, reusable components that you can just snap together to build the exact fuzzer you need for the job. Okay, so to get how this works, you have to think of a fuzzer as having a few core jobs, right? There's the corpus, which is just where you store interesting test cases. There's a scheduler that decides which one to test next. You've got a mutator that smartly changes an input to create a new one, and then a feedback mechanism that decides if a test run was interesting. Now, in the old days, all these pieces were baked together into one big program. But LibAFL, it provides them as separate, totally swappable blocks. And here you can see the official blueprint. Now, don't worry about following every single line, but you can really get the core idea here. You see these distinct components, like the scheduler and the feedbacks, are all designed to just plug into a central fuzzer loop. It's a perfect visual of how everything is truly modular by design. Okay, so what does this all mean in practice? How does this whole Lego box idea actually help researchers build something better? Let's take a look at how this theory really translates into a much more powerful tool. I mean, the contrast is just night and day. The old way, you'd start with this giant blob of code and pretty quickly get locked into your own custom version. But the LibAFL way is all about composing things. You can literally pick the best scheduler from one research paper, combine it with the cleverest mutator from another, and just snap them together. You're not reinventing the wheel anymore. You're standing on the shoulders of the entire community, using all their best ideas. And you know, the proof really is in the pudding. Using this exact framework, the authors were able to integrate and test techniques for more than 20 different research papers. I mean, that's something that would have been an absolute engineering nightmare before. For the very first time, they could combine years of all that fragmented research into one single powerful tool. So, after building this awesome new fuzzer from all the best Lego blocks they could find, the big question was still out there. Did it actually work any better? Was this whole new approach actually ready to create a new champion? And the answer was a resounding yes. They put it on FuzzBench, which is the industry standard test for this stuff, and the generic fuzzer built with LibAFL just clearly outperformed the existing heavy hitters, tools like HonggFuzz and AFL++. Really, the final number says it all. FuzzBench calculates this average score to compare everything, and the LibAFL-based fuzzer hit 98.61, beating every single other tool in the test. This wasn't just some small, theoretical improvement. This was a massive, measurable leap forward. So the outcome is pretty crystal clear. By creating this modular framework that lets researchers actually combine their best ideas, the LibAFL project didn't just solve that big fragmentation problem, they used the solution to build a fuzzer that is demonstrably, provably better. And that really leaves us with a fascinating final thought. This whole thing isn't just about building better tools, it's about accelerating the pace of discovery. Now that we have a framework where the entire security community can finally collaborate and build on each other's work, well, the next critical bug in the software you use every single day might just be found a whole lot faster. What will they find next?